Welcome. I am Anandadash Gupta and this is the second lecture of PH 4105 Advanced Mathematical Physics. This is a course on differential geometry and algebraic topology which is offered to 4th and 5th year students majoring in physics at the Indian Institute of Science, Education and Research, Kolkata. In the last lecture, we had seen how we could generalize our age-old notion of calculus on the real line to functions which take you from Rm to Rn. That is, from a bunch of m real numbers to a bunch of n real numbers. We had explored the notion of differentiability via the notion of a differential, a linear map df of x which carries Rm to Rn, such that the difference between f of x plus h minus fx and this value which d of f of x has on the change h in the argument of f is small for small h. The smallness is captured by the fact that if you take the difference, take its modulus and divide that by the length of the displacement h in the argument, this ratio goes to 0 in the limit where mod of h goes to 0. And this linear map df at x, if it exists, is called the differential of f at x. And so this differential is a linear map which carries a change in the argument to an approximation of how much the function itself changes. We have also seen that if this notion is to make sense in a more general setting where the function is not from all of Rm to all of Rn, but from just a subset of Rm to Rn, then this subset should be an open set of Rn simply because you should be able to make sense of changing x by an amount h, and this h can be a vector in any direction in Rn. And because of this, for every point in the domain U, you must have a way of moving in all possible directions. In other words, you should be able to put a ball surrounding that particular point entirely inside U. This notion of differentiability is a generalization from the notion of the differentiability of a function on the real line, but this is not enough for physicists. We need to be able to do calculus or even more general sets. So the question that naturally arises is, how do we extend this to more general sets? And the answer is through manifolds. The basic notion of a manifold is what we are going to explore in today's lecture. This notion of manifolds, or to be more precise, differentiable manifolds, provide us with a more general setting for calculus, as we have just said. To begin with, the manifold M is a set, but is not just a set. In order to qualify as a manifold, you need additional structure on this set. And to understand what this structure is, we will start with its basic component, a chart. A chart, u, phi on M, is an ordered pair. That means, of course, that you need two things to make a chart. The first of these is U, which is a subset of M, and the second is a map phi which carries U to Rn. But any phi or any U will not do. You will need additional conditions. And the additional conditions you need is that this phi has to be a one-to-one map. So no two different elements of U will give you the same tuple of numbers in Rn. And the second condition is something which we should expect from what we said a while ago about differentiability of functions on subsets of Rm. Phi U, the image of phi under U, must be an open subset of Rn. Now, given how bad my drawing skills are, I don't think the old adage that a picture is worth 1,000 words will quite be correct in this case. However, a picture, no matter how badly drawn it is, would still help in getting some of the basic ideas across. So here goes. I've depicted this set M by this region bounded by this orange curve. The subset U is a region bounded by this magenta curve. Of course, in some situations you could be the whole of M, but usually it is a proper subset, as we have depicted in this case. The map phi takes points in U and pulls them onto Rn. In fact, it maps this region U, all of these points in the region U, taken all together, inside this thing which I have depicted by this dotted curve. This is my phi U set. The dotted curve simply is a reminder that the boundary is not really inside this set, it's an open set. Specifically, the point P has been pulled to this blue point here in Rn, which is of course called phi of P. Now this point phi of P is a point in Rn, so it can be depicted by n real numbers. And these n real numbers can be called x1p, x2p and xnp. And this helps us understand how a chart phi assigns coordinates x1, x2, xn to every point P in U. And these xi's, which are actually maps from the set M to the set of real numbers, is called the ith coordinate function for the chart U, phi. Basically, x1, x2, x3 are the numbers that we have always called coordinates for a point wherever we have used a coordinate system. It is the job of this chart U, phi to assign coordinates to arbitrary points in a manifold. Of course, a particular chart U, phi can only assign coordinates to a points in U. If U does not cover the entirety of M, then you might need more than one chart to help you assign coordinates to every point that you are interested in. Now this relationship between the point P in U and the numbers x1p, x2p all the way up to xnp actually goes both ways. Since phi is a one-to-one map, it becomes invertible if we were to restrict the domain from all of Rn to just phi of U. And in that sense, we can find a map phi inverse which maps phi U into M. And what this means is, if you give me a bunch of numbers, coordinates of a point in phi of U, that bunch of n numbers will actually correspond to unique point P in U. In other words, not only do points have unique coordinates, coordinates are connected to a unique point, at least as long as you are sticking to a given coordinate system. Now the whole point of introducing a chart on a set M is that it will give us our first step towards creating a differential structure. What that means is that charts gives us a way of talking about differentiability on this set M. In order to see how that works, let us now consider a function f from M to R, the set of real numbers. Given such a function f from M to R, we are now in a position to answer the question, is f differentiable at a point P if we have a chart U, phi with P inside the set U? The way in which we will answer the question is by looking at what I call the proxy function, capital F. This is a function f composite phi inverse, which is a map from phi of U to R. And remember, phi of U is an open subset of Rn, so we are really now looking at a function from an open subset of Rn to R. And it is quite legitimate to ask ourselves the question, is capital F differentiable at the point phi P? Of course, for all this to make sense, P must be contained in U. So, if you have only one chart U, phi in your hands, and you want to talk about differentiability of a function at a point which is not within U, then you are out of luck. We will see what to do in that case soon. But for the time being, let me once again put my drawing skills to test and try to show you what this really means on a picture. This picture is exactly the same as the one that we saw a while ago, except for a few additions. In addition to the map phi, which takes points P to phi of P, in fact it does so to all points in U, but I am focusing on a particular specific point P here, we have also added with this dashed line a depiction of the inverse function phi inverse. So given this point in phi of U, which remember is a subset of Rn, phi inverse carries you back to the point P on the manifold. Now this manifold comes with a function small f which maps points on the manifold to the real line. And if you look at the function f composite phi inverse, is actually f after phi inverse. Remember, phi inverse gets to act first and then f acts on it. So what that does is takes this point in phi of U, let's say the specific point phi of P, first applies phi inverse on it to get to P, then applies f on it to get to R. So f composite phi inverse, our function capital F, really takes this bunch of real numbers, this x1p, x2p, xnp, and maps this all the way to a real number line. So see what exactly is going on here. Let me point out that if you apply f on x1p, x2p, dot xnp, all the n coordinates of the point P, what you are really doing is applying the function f composite phi inverse, which is my capital F, to phi of P, which is nothing but this bunch of n real numbers. And that, of course, is nothing but f composite phi inverse composite phi acting on P, and that obviously is f of P. So the function f at the point P has a value. Capital F is a function from an entirely different domain, the domain being phi of U, and maps it onto the real line. So capital F is an entirely different function, but it has the same numerical value if you give it the arguments x1p, x2p, x3p, xnp, as small f does at the point P. Now the point behind doing all of this is that although small f was a function from a set M to R, and we don't really know how to do calculus on an arbitrary set M, this proxy function capital F is a function from an open subset of Rn to R, and we do know how to do calculus there. So what we have managed to do is replace a problem which we did not know how to handle, the question of differentiability of a function small f on the set M, to a question that we can handle, the question of differentiability of a function, the so-called proxy function, which acts on an open subset of Rn and takes you to R. Now you must, of course, be worried about what to do with points which are not included in U, and obviously for them what we will need are more charts. And if you really want to do calculus all over the set M, what you will need are charts which cover the entire set. And such a collection of charts which cover the entire set M will be essential in talking about the differential structure on M. But for the time being, let me go back to our single chart U, phi, and let us take a look at a few examples of that. Before that, let me issue a clarification / correction of what I said a while ago. I realize now that I may have referred maybe a couple or so times to the set M as the manifold M. That is really putting the cart before the horse. The set M is not really a manifold, at least not yet. A set M becomes a manifold if you get a full-fledged differential structure on it. A structure that will allow you to do calculus all over the set, not just on a particular single chart's domain. Strictly speaking, M is not the manifold even then. The manifold is actually the set M in addition to the differential structure on it. However, we very often deliberately confuse the two notions. We talk of the underlying set M as the manifold, especially when there is no possible confusion about what differential structure we are talking about. So in a way, I have gone a bit ahead of the current state my lectures are in. I have referred to the set M in anticipation as a manifold, something that we can legitimately do only after a complete differential structure has been created on M. Now, let us go back to this issue of building up the differential structure in the first place, with its very first step, creating one chart on a set M. Our examples will begin with a very simple one, indeed a trivial one. The first example, as I said, is trivial. Here M is nothing other than Rn itself, a bunch of n real numbers. In this case, it should be pretty obvious that we can take the chart u, phi to have a domain U which is the entire set M, that is Rn itself, and phi can just be the identity map, which will map the n real numbers which form a point on M to exactly the same n real numbers. So Rn, id is a chart on Rn. Here, the coordinates assigned to a point P are trivially nothing other than the components of P. So the coordinate functions x1p, x2p, x3p, xnp together make up nothing but the identity map, something which maps P to itself. But before we move on to our second, slightly more non-trivial example, let me emphasize two important points. Firstly, this chart Rn, id does satisfy all the properties of a chart. One, the map id, which is phi for us, is 1 to 1. That's pretty obvious. And two, if you apply the map id on the entire set U, in this case Rn, you of course get Rn. And this is an open set in Rn. So the two basic properties which a chart must satisfy is definitely satisfied by our chart. This was trivial, but I am just doing this to emphasize that this is a check that you will have to carry out in each and every case. Now, having seen this really trivial example, let us move on to the next example, which is actually almost as trivial, but maybe would have some surprises for you. We are again going to talk about Rn, but specifically we are going to talk about R2 because that's simpler. What I am saying here can be generalized to Rn, but let's stick to R2 for now. And what we are going to do is use, instead of the good old Cartesian coordinates, something else which we are also pretty familiar with, the so-called polar coordinates on R2. Now, as you are all familiar, the polar coordinates map the Cartesian coordinates x, y of a point to r and theta, where x is given by r cosine theta and y is given by r sine theta. This is really not the map phi, it's rather its inverse, because x and y has been given in terms of r and theta, and you have to solve these to get back r and theta, the coordinates, in your new chart. Now all this is fine, but it is obvious that this map has a problem at 0, 0. The problem is actually one of plenty, in the sense that the point at the origin, which is uniquely given by 0 and 0 in Cartesian, suffers from a problem of plenty in polar coordinates. R is definitely 0 there, but what about the value of theta? In fact, any value of theta will do. In other words, the map which goes from r theta to xy, the inverse of this map phi, is actually not 1 to 1. Frankly, as far as our map phi is concerned, the one which goes from xy to r theta, at the origin this is not even a well-defined map, simply because one input 0, 0 will lead to multiple outputs. In fact, infinitely many outputs, 0, theta with r equal to 0 and any value of theta whatsoever. So our chart would fail if you tried to use it all over the plane, simply because this particular function phi that we are talking about is not well defined at the origin. Well, of course, what you could do when faced with such a situation is drop the offending point from your domain. That is, try the domain U to be R2 set minus the origin. That is, take away the origin from R2, take away this point marked red, and use the rest of the plane. Now, there will be a problem with that, because if you were to try to associate a value of theta to a given point, then this point can have a value of theta, some definite value. But if you were to come all the way around and get back here again, you will again get another value of theta, which is 2 pi more. In fact, you can go all the way around again and get 4 pi more, or go the other way around and get 2 pi less. So having said that, this again causes a problem. Your function becomes multi-valued, which essentially means it's not a function at all. The way to prevent that would be to restrict your image here. So one possibility could be that you just say the theta goes from 0 and just falls short of 2 pi. That is, you will not allow theta to take the value 2 pi again if you have included the value 0. In fact, the 0 value is arbitrary. You could have done it for any other theta. You could have included theta starting from alpha and going all the way round and just stopping short of alpha plus 2 pi. However, if you did use this particular map, which is essentially what we use when we say polar coordinates, then you will again run into a problem. Here the problem will not be one of one-to-oneness or well-definedness. The map will be perfectly well-defined. It will be one-to-one. However, the image of the domain phi of u in this case will be the following. R can take any value, any finite value, that is, will not be able to take 0, so that's why it's open-ended here. And of course, it takes any number, so it's 0 to infinity, the open interval. This is for R. What about theta? Theta will run from 0, and 0 will be included, and go all the way up to 2 pi, but fall short of 2 pi. So you have a semi-open interval here. Unfortunately, this set phi of u is not an open subset of R2, which is what we are looking for. In particular, a point here on our so-called x-axis, or in this case the theta equal to 0 line, any point here will lead to a boundary point in the image. In the image set, what you have is actually 0 is an endpoint, so negative values are not allowed. And that means that you do not have an open set in this case. So while our proposed chart with u as the plane minus the origin and phi as the standard polar coordinates actually do satisfy one of the properties of a chart, that is, it is one-to-one, it actually fails to give you an open set as an image of u. So this is really not a valid chart. So things are a bit more complicated than you would imagine. This is not really that difficult to get rid of. All you need to worry about is the points r, 0, which actually were leading to these boundary points in phi of u. What you could try to do is just imagine that you have dropped them. So let's just say I take a Caesar and cut out the x-axis. In other words, what you are talking about now is a domain where u is not the entire R2, is the entire R2 without the positive x-axis and of course the origin. So x greater than equal to 0, y equal to 0, all these points are taken out. Now if you were to use our polar coordinates, the phi of u will come out to be rectangle, which goes from 0 to infinity along r and 0 to 2 pi along theta, but with all the endpoints excluded. So this will be a genuine open set. Now of course, one bad thing that will come out from this is immediate. In fact, we already saw that the moment we had to drop the origin, polar coordinates cannot cover the entire plane. A single chart in which you are using the polar coordinates will not actually work for all of R2. In fact, many of the problems that we face at theta equal to 0 or r equal to 0, when we try to use polar coordinates, especially when we look at differential equations on the plane and meet singular points, actually can be traced back to this fact that, frankly, the polar coordinates are not good coordinates there. We will have more to say about this later. For the time being, let's move away from just the plain old plane and go and talk about something a bit more esoteric. Our first so-called esoteric example is actually quite a simple one. A set which is not a bunch of points for a change. We are going to talk about the set of all 2 by 2 real matrices, so-called mat 2, R. Now, any 2 by 2 real matrix, of course, has this form A, B, C, D, with A, B and C, D arranged in a 2 by 2 array. And here, it's rather obvious what a choice for U and phi will be. You could just choose U to be all of the M, that is, all 2 by 2 real valued matrices will be covered by U. And the map phi should be nothing but U goes to R4, where A, B, C, D, the matrix, just gets mapped onto the 4 numbers A, B, C and D. In other words, you just take the elements of the matrix and put them as a row vector or a column vector, as you might want to represent points of R4 by. Now, this map is obviously 1 to 1, and phi of U, in this case, is obviously all of R4. Any real number that you can think about can be one of the elements, and if you take a look at all the matrices together, you would be able to cover all points in R4. And that obviously is an open set in R4. So our M here is a manifold which is actually globally, in its entirety, mappable to R4. So there's very little difference really between the set of all 2 by 2 real matrices and the set of all tuples with 4 real number entries. Our next example will again be a set of matrices. The set is called GL2R, and it is the set of all 2 by 2 matrices, all matrices A belonging to mat 2, R, for which the determinant of A is not 0. Now, as you are almost certainly aware, GL2R actually forms a group under matrix multiplication. So, this particular set, the set of all invertible matrices which are 2 by 2 and real, is actually more than just a set, it's also a group. And this will be our first example where we can see a group in the form of a manifold. Well, strictly speaking, that's really not true, because Rn, something that we have seen before, actually is already known to be a group under addition. But frankly, this is the first really non-trivial group that we are looking at, and we are actually taking a look at what is called a group manifold. Now, what will the chart be here? Well, notice that our matrices are actually of the same form as before. They are A, B, C, D, where all the numbers A, B, C and D belong to the real number. So the tuple A, B, C, D is an element of R4, with the restriction that AD minus BC is not equal to 0. So let us try first whatever we did with mat 2R. We can just take U to be all of M, in this case all of GL2R, and phi simply to be the same map, something which maps U to R4, and the map is simply A, B, C, D goes to the numbers A, B, C, D arranged in a tuple. Now, is this 1 to 1? It obviously is. In fact, if the final end product is given, you uniquely get the matrix from which you could have got that bunch of 4 numbers. So 1-to-oneness, one test is passed. What about openness of phi of U? In the previous example where we used mat 2, R, the openness of phi of u was beyond question because phi of u was simply R4. Here, what is phi u? Phi u is actually not all of R4, despite the fact that phi maps a matrix to a tuple in R4. There are certain tuples which are never part of the image. The reason being, all our matrices are invertible matrices, so they satisfy AD minus BC is not equal to 0. And so you can only get tuples for which AD minus BC is not 0. In other words, our phi of u is R4 from which all tuples for which AD minus BC equal to 0 have been taken out. R4 set minus this particular set of all such tuples. So now that phi of u is not all of R4, we must ask ourselves the question, is phi of u an open set? Now, if we were to use certain results from differential geometry of surfaces, you would automatically know that this set here, the set given by AD minus BC equal to 0, is what is called a level set. It's a hypersurface in R4. And if you take away a hypersurface from R4, what is left is an open set. So we could just use that result and establish that our u comma phi is actually a genuine chart. So if you are familiar with the result that I've quoted right now, or you are not really interested in going through the nitty-gritty details for this particular proof, you can simply skip on to the next example. What I would like to show you, however, is how you can establish that phi of u is an open set without having to appeal to some standard result from mathematics which you may or may not know. I would like to explicitly show that this particular set is open by showing that all its member points are actually interior points. Now, I do not quite remember whether I have stated this before. I have certainly implied it. Whenever I say phi of u is an open set for a chart in any manifold, open set of Rn that is, I mean that it is open according to the standard topology of Rn. In other words, every point in such a set has to be an interior point. You should be able to put a ball of some finite radius around that point which will be contained entirely inside the set. Is that the case here? To see this, let us consider an arbitrary point x0 in the image phi of u. Now this point obviously is not in the complement of the image phi u c, and so we can define a distance of the point x0 from phi u c. Phi u c is of course this particular set of tuples a, b, c, d belonging to R4 with AD minus BC equal to 0. To define the distance, what we need to do is to take any point x in phi u of c, find the standard Euclidean distance of that point from x from x0, and then find the infimum of these bunch of distances as x ranges all over the complement or this hypersurface with AD equal to BC. Now it is intuitively obvious that this d is a positive number. If we accept that, then the proof becomes very simple. All you have to do is take a ball of radius d, this distance, surrounding x0, and it's easy to see that bx0d cannot intersect phi u's complement. In other words, since all points on phi uc are at least a distance d away from x0, bx0d, which is a collection of all points within a distance d from x0, must have no point in common with phi u's complement. And so, this particular ball bdx0 will be a subset of phi of u, and then you're done. This point x0 is an interior point because you can put a ball around it which is entirely contained within our set phi of u. Hence, phi of u is open. So that proves what we wanted to prove, that phi is a one-to-one map we have already established, and phi of u is an open set. That's what we have now established. So our proof that this is a chart which covers all of GL2R actually is done. But there's just one small nagging point here. This d that we have defined, the distance of the point x0 from this surface with AD equal to BC, well, it's a infimum of a bunch of positive real numbers. But we do know of plenty of examples of cases where the infimum of a bunch of positive numbers is not actually a positive number. The traditional example for this, of course, is the set 1/2, 1/3, 1/4, and so on, the set of reciprocals of all natural numbers. This, of course, consists only of positive real numbers, but the infimum of this set, as anybody who has studied elementary mathematics knows, is the number 0, which is not a positive number. And remember, 0 is not a valid value for the radius of a ball. A ball has to have finite non-zero radius. So there is a gap in our proof that we have given so far. We have not yet shown that d is a positive number. Now I will try to take a few minutes to show a way in which you can prove that d really is a positive number. Now you might very well think that this result is obvious and I should not bother spending time on this. But let me assure you that details of this kind can end up being the deal breaker in many other cases. It's not in this case, as we will soon show. So the question that we are really asking ourselves is d really positive? And to show that it is, what I'm going to do is explicitly calculate, or at least show you a way of calculating what the d is. To do this, I'm going to take an arbitrary point x on our surface phi u c and minimize the distance of the point x from the point x0. I'm going to use elementary calculus for that. I need to minimize x1 minus x10 whole square plus x2 minus x20 whole square plus x3 minus x0 whole square plus x4 minus x40 whole square. And what complicates matters for us is that the point x is not an arbitrary point. Had it been an arbitrary point, then the obvious solution to this would have been x1, x2, x3, x4 all have to be equal to x10, x20, x30, x40, and the distance would have been 0. However, we do have this result, this constraint, that x1, x4 minus x2, x3 has to be equal to 0. This is what ensures that the point I'm talking about is actually a point in phi u c. So this is a problem of constrained optimization. You have to minimize a quantity subject to a constraint. The standard way to do it will be using Lagrange multipliers. Now I'm going to skip over the details of the calculation. You can definitely fill them in yourselves. But the way to use Lagrange multipliers would be to take the differential of this expression and of this expression, multiply the differential of this by an undetermined, at least as yet undetermined multiplier lambda, add the two differentials together and equate this to 0, and then look at the individual coefficients and check whether that is going to be 0 or not. So this actually leads to 4 equations which you can get just by looking at the coefficient of dx1, for example. I get x1 minus x10 from here plus lambda x4 from here. So x1 plus lambda x4 minus x10 has to be 0, and that gives you this equation. Similarly, we can write down the other 3 equations and you can easily see that they can be solved for x1, x4 and x2, x3 in terms of x10, x40, x20, x30 here. Now, just solving this does not tell us x1, x4, x2, x3 simply because lambda is as yet undetermined multiplier. But you can figure out what the value of lambda is by now looking at the constraint. Remember, our point x is a point on phi u c. So it has to satisfy x1, x4 minus x2, x3 equals 0. And if we take our solution here and just plug it in the equation x1, x4 equal to x2, x3, this gives us an equation for lambda. Note that in this stage, I have divided by the quantity x10, x40 minus x20, x30, and that is a legitimate thing to do because this number is not 0, since remember x0 is not a point on our surface. Now, this quadratic equation can be solved for lambda. The very important point that I want you to check here is this number 1 here ensures that a root for this cannot be lambda equal to 0. In other words, this set of equations will not end up being a trivial set of equations where x1, x10, x2, x20, etc. come out to be equal to each other. Since lambda is not equal to 0, we see that x1, x2, x3, x4 is definitely different from x10, x20, x30, x40, and therefore the distance which you calculate between these 2 points, which is going to be the minimum distance or the point x0 from the surface, has to be a non-zero number. Now there's only one thing to show before we can actually wrap this whole thing up, which is that this lambda is actually a real number. But after all, if the only possible solutions for lambda here are complex numbers, we don't really have any point which satisfies our condition. That's pretty easy to show. I will not again go into the details. You can easily show that this quadratic equation has a positive discriminant. Elementary algebra will show you that. And hence, lambda has real roots. So for every x0, we can find a point x, at least one point x, which is different from x0, which is at a minimum non-zero distance from it. And therefore, our d is really non-zero and our job is done. If I am being very honest, I should confess that the proof that I gave you right now has a very tiny gap in it. Well, let me leave that as an exercise for you. Try to figure out what exactly was the gap in the argument and then check for yourself that that is really not going to invalidate our result. So far, we have seen a few examples of sets on which we can have charts defined which make the set, at least locally, look like a subset of Rn. Now, in all our examples so far, we have been able to find a single chart which will cover the entire set in question. Although we did have an example of R2 with the polar coordinates where the chart did not cover the entire set, we could of course have used Cartesian coordinates there and covered the entire set with that. However, there will be examples, as we will see in the next lecture, of sets which cannot be covered by single charts. And so, you will definitely need to talk about multiple charts which end up covering the entire set. And such a collection of charts will give us what we call an atlas, or to be more precise, a subatlas. We will have to worry about compatibility between these charts, and that's going to be a big point in deciding whether we actually have a valid differential structure in our hands. But all that will have to wait for the next lecture. Bye till then.